hypothesis testing. Let's look at the following example. A random sample of 24 ducks of a certain species is taken from a lake. The sample has a mean weight of 1.6 kilograms with a standard deviation of 0.25 kilograms. Assume that the weights are normally distributed. Using a 0.01 level of significance, test the claim that the mean weight is not 1.4 kilograms. As we start a problem at this point of the semester and in this point of the class, one of the things that you need to do is to determine what type of problem it is. And we can do that by looking at first this phrase right here, test the claim. When you see that phrase right here, test the claim, that tells us that we have a problem that is a hypothesis testing. We're testing something. We're testing a claim. That tells us it's hypothesis testing. And then we also see the words here, mean, and then up here again, mean, and that tells us that we're testing the claim on a mean. And those two things tell us that we're testing the mean weight and that we're testing the claim on that mean. And from there, we can then go to the next step of the problem, which is to decipher and to break this problem down into bits. As we look at this problem, we want to take and rewrite this problem and write it down and to take ownership of this problem by writing down the information. The first sentence says a random sample of 24 ducks that from a certain species of lake. Well, we don't care where they were from or that they're a certain species, but we do care that there were 24 of them, and that's a number. So that's our sample size. N represents our sample size, so N equals 24. Then the next phrase says the sample has a mean weight. So sample and mean. Well, the symbol for a sample mean is X bar, and so that X bar then is 1.6 kilograms with a standard deviation of 0.25 kilograms. Well, that implies that it's the sample's standard deviation, so that's 0.25 kilograms for the sample standard deviation, remembering that S is the symbol for a sample standard deviation. And again, I'm breaking the problem down step by step and rewriting the information as I come across it. The next phrase, or the next sentence says, assume that the weights are normally distributed. Well, we have to know that to be able to do the problem. Nothing new there. The next phrase, using a 0.01 level of significance, that's our alpha. That's an important piece, so I'm going to write it down next. It says test the claim. Well, in hypothesis testing, the claim is very important. So I'm going to write the word, not only using symbols, but I'm going to write the word claim so I know what I'm talking about. And since a claim, and this is important too, the claim is always about the population, something that we want to know about everything. And so that always uses the population symbol. So we're saying something about the population. Claim that the mean is not means not equals, is not equal to 1.4 kilograms. And now I've deciphered the problem and I'm ready for the next step. Well, of course, I don't have enough room here, so by the magic of editing, we now are from a PowerPoint to a written sheet of paper with the same problem and the same information written down. And what we're going to do now is I'm going to transfer this information to a blank sheet of paper where I have room to work this information out. I'm going to keep this sheet of paper handy in case we need to refer back to the original problem. But it's just the same information that we just had. Let me reach across here and get my pencil. And it's the same information. The n is 24. The mean is the sample mean. Remember, X bar does refer to your sample size. The sample mean is 1.6. The sample size is 24. The standard deviation of the sample is 0.25. The level of significance that we're using is 0.01. And we're testing the claim that the mean is 1.4 kilograms. Or excuse me, is not 1.4 kilograms. Now, next on the list of things that we need to do, after we've determined that it is a hypothesis testing, after we've written down the information from our problem, the next thing we want to do is to make sure that we stay organized. Each teacher here at Walters State organizes themselves slightly differently. And you want to match what your teacher's doing, because that is what you're seeing most often in class. That's what you've seen in your lecture or your PowerPoints or whatever that your teacher has provided for you, your quizzes and so forth. And that's what you're going to be tested on. So you want to match their organization. If your teacher doesn't care, then you can match my organization. I try to keep mine general enough that it'll match whatever your teacher does, and so that I'm not contradicting anything that any of our teachers do. If something I do does contradict your teacher, always follow your teacher, not me. But the next thing we want to do is to label our HO and our H1. And so I kind of call this this would be my first step. And I'm just going to label it 1 as my organization. Here's my first step. I'm going to label HO and H1. That is our null and our alternate hypothesis. And remember that our null is always the equal to. And I'm going to write this in a different color here. This is not part of your normal problem, but just as an aside, actually I'm even going to put it on a post-it note here. Your null is always going to be that the mean is equal to, the mean is greater than or equal to, or the mean is less than or equal to. And again, some of your teachers will tell you that it's always the top one, and so I may be contradicting them by saying these two things. So if your teacher says it's always equal to, use that, but some of our teachers also use these. So you've got one of these 3 symbols that you can use, and some of them will always use this. Our alternate can be that the mean is not equal to, that the mean is less than, or that the mean is greater than. Notice that the H1 never has a condition of equality. There are no equals. This is not equal to, less than, and greater than. So we have here conditions that are not equal. No equals there, not an equals here, and not an equals here. And notice that this would be the mean here as well. Now, if we were talking about proportions, we would substitute the mean, we would substitute proportions there for the mean. And notice that the way I've written these, that they correspond to each other as opposites. The opposites of greater than would be less than or equal to. The opposite of less than would be greater than or equal to, and the opposite of equal to would be not equal to. That is designed to be that way. These are paired hypothesis, null hypothesis, and alternate hypothesis. They have to go that way. And so there's a little aside about that. Okay, now for us, we have that the claim is not equal to. Since the alternate is the only one that can have a condition that has the not equal to, this must be the alternate hypothesis. And for purposes later on about how to make my statement and conclusion, I'm going to remind myself that that's the claim. Then the null must always have an equal to, so the opposite of not equal to is equal to. That is the null. And for me, the second step involves drawing a picture. By drawing the picture, I get a good view of what's going on with my problem. So I draw my bell curve for my normally distributed, and we always want to draw our alternate hypothesis. That is what we're going to draw and to shade on our bell curve. So not equal to is a two-tail test. If it's not equal to, it's not a left tail test for less than. It's not a greater than, so it's not a right tail test. It's not equal to. It could be on either side. So I'm going to take here and shade. Okay, the next thing to do is to take our significance level. Well, I don't have to go back and look in the problem. I've got my significance level right here. And I'm going to take that 0.01 and divide by 2, and that gives me 0.005. Now, why do I divide by 2? Because I have two tails. I have 0.005. That 0.01 is my alpha, and that tells me how much area I want to shade. And I'm shading equally on two sides, so I have to divide that by 2. Now, the next thing that you want to do is to grab your table. And we need to use the T table. And I'm going to bring down a T table right here. And it's not as clear as I would like it. So you're just going to have to bear with me. But there is the 0.005. And over here is our degrees of freedom. Remember that we do not go down to our sample size of 24, but we go n-1, which is 23, and come across and down. I'll give that a second and see if I can get that to focus in. There we go. There, I got it to focus a little bit better. There's your 23, and there's your 0.005, and life is good. And we get 0.2807. Now, what does that 0.2807 mean? Oh, wow, much better. That means that we have 0.2807 here, and symmetrically we have negative 0.2807 on that side. Okay, next on the list of things to do, now that we've got our picture drawn of what we're doing, and remember what this means is that if our sample falls inside on here in this non-shaded region, this is the do not reject region, and over here is the reject region, and over here is a reject region. So we would reject it if it's on either end, but we do not reject it if it's in the center. See if I can get that to come in back in focus a little bit. Okay, next on the list of things to do is to see where our sample actually falls, and that's just doing our t formula, which is x bar minus the mean over the standard deviation divided by the square root of n, since we have a sample size. We take our sample, which is 1.6, subtract what we're comparing it to the mean, 1.4, divide it by our sample size, divided by the square root of n, which is 24. Notice we don't use the degrees of freedom. And I'm going to show you how I type that into the calculator. And trying to get this where you can see exactly how I type it into the calculator. Okay, I'm going to type in 1.6 subtract 1.4. Notice I do not use the parentheses around that. I just go on and hit enter and get the top done. In other words, order of operation says do the top, do the bottom, and then divide. So I do the top, divide, then parentheses, because now I need it to do the bottom. And to do the bottom, I need it to do it all together. And since I'm going to do that, I need parentheses around the bottom, and I need to, I need to hit the standard deviation, which is 0.25, divided by the square root of n, which is 24. And because I started a parentheses here, I'll need to end one here. Notice there's one set of parentheses around the square root and one around the bottom. If you forget this last parentheses, it's okay, but if you forget it around the top and don't hit enter, it gets it all messed up. So that's why I like to hit the top and then press enter and get that top number and then do the bottom here, because it's a little more forgiving as long as you remember this first parentheses. And that gives me a z-score of 3.919. And I take it out 3 decimal places because this is 3 decimal places. Now, what does this tell me? This tells me on a scale, if 0's here and 2.8 here, that this is somewhere here. It's in the shaded region. Therefore, I reject. So I'm going to come up here and write what I do. I'm going to reject HO. If I reject HO, that means I'm going to support H1. And the claim is here, so my real statement is that I've got enough evidence to support the claim. So that's where I'm going to come back in and write my sentence. And for some of our teachers, that's the most important part. So you want to be sure that you write it out in completion using a 0.01 level of significance. And that's kind of like always your beginning phrase for that. And you just fill in the number that you're using there. Okay? Then the next phrase is always the same as well. There is enough evidence to. Now the difference is sometimes you say there is not. If you do not reject, you put a not here. A not there means a not here. If there isn't a not, then you don't have a not. So I didn't have a not. I rejected. So there is enough evidence to, and what am I doing? I'm supporting the claim. If the claim had been up here, I would have been rejecting the claim. But the claim is here, and I'm supporting it. So there is enough evidence to support the claim that, and here's where it gets really easy. You take your problem and you go and find the phrase, claim that the mean weight, and if I want to be fancy, I want to say of the ducks is not 1.4 kilograms. And you just copy it word for word from the problem. And that's my conclusion. Now, this is the traditional method. And again, this would have been step 3, and this is step 4. Some teachers call this, I guess, this step 4 and this step 5. Depending on how you want to number it. But that's your conclusion. Now, I want to show you in one other thing on the calculator, and that's called the P method, or the probability method, the p-value method. And I'm hoping that the calculator all shows up. Otherwise, I have to tape this whole thing kit and caboodle again. And so I'm going to hold the calculator right here in the center, and I hope that you see most of the calculator. What you want to do on the p-value is you're using the calculator to get a probability. And the first step you want to do is to go to your stat button. And you want to go over, you're doing a hypothesis test. So you're going to go over and arrow over till you select test. And then you're going to decide whether you're doing a z-test or a t-test. Well, we have a sample standard deviation and a sample size of 24, so we're going to select a t-test. And we're going to select stats, because we're going to put our stats in. And actually, I already have the stats in here, but we'll go over how we decided that. Mu sub 0 is really for our null hypothesis. And remember, everything we've done here, what we're going to talk about, I'm going to turn this paper, fold it in half here so we can get that. We'll have done this first part, which is we'll have done step 1, and we'll know that the null is talking about 1.4. We'll know that the X bar, we'll have written down our information, and we'll know that it's talking about 1.6. We'll have read our problem and written down our information and know that the sample standard deviation is 0.25, that our sample size is 24, and that we're comparing it against our alternate, and that's what they want down here, and that is that it's not equal to. And notice that's just highlighted. If I wanted to highlight another one, I just arrow over and then I'm pressing enter. But I want the first one highlighted, and I'm just pressing enter. And so it's highlighted. And then I'm going to press calculate, and it gives me these numbers here. And the numbers that it gives me is, it gives me my t-value of 3.919. And I'm going to flip my page over and to remind you that that's the same t-value we calculated. So it's a good way to check your t-value. And it gives me a p-value of 6.874338 E negative 4. And remember that E negative 4 simply means that you need to move your decimal back 4 places. So that's 0.000. There's 3 places. And the 6 counts as 1 as well. 87. And that's my p-value. And since 0.000687 is less than the 0.01, and why are we comparing it to 0.01? Because that's my alpha there. And so I'm saying my p is less than my alpha. And what we're saying here is that we want our p-value, the probability that this happened just by chance, is small, and it's smaller than my significance level. We're going to say anything less than 0.01 is unusual. So this is unusual. Whoops, I can't spell unusual today. Let's start over. Unusual. And since it's unusual, we're going to reject that it happened by chance. So we're going to reject HO. And since we reject HO, we support H1, and that gives us the claim, and we're back to where we are. So the p-value basically skips calculating the step 3 and drawing our picture by hand and finding the 2.807 and the negative 2.807 and making the comparison of this number to this number. It compares a probability to a probability and lets the calculator find that value for us. So that's an example of doing hypothesis testing. I hope this was helpful. Thank you for watching.